Good evening, students. Today I'm going to start another session of week 5, and we will be discussing lectures and problem solving questions in the course Nanotechnology, Science and Application. Here I'm your presenter Akshita Sharma from IIT Delhi, and in between, if you have any doubt, you can raise your hand and ask the questions. And I should tell you that it is an interactive session, so I request that you should also be interactive in this session and answer the question if you know them, and if you do not know them, you can clarify your doubt. That is why this session is there. Moving on with the assignment questions of week 4, we will discuss the assignment this week. So first question says that an example of strengthening mechanism is, your options are grain size reduction, strain hardening, solid solution strengthening, or all the above. Which of the option is correct? Is it option 1, 2, 3, 4? Which of them is correct? All of the above. Okay. All the options help in strengthening the mechanism. You have you have read about the stress and strain properties. We have discussed yield strength, and to improve the yield strength, we should do nano sizing, which means grain size reduction. We should introduce more strain, and, and we should also do solid solution strengthening. Got it? Now moving on to the second question. As grain size reduces, which of the option is right for the reduction in the grain size? What is the effect? Your options: dislocation movement are impeded, strength decreases, grain boundary volume reduces, or both A and C. Impede means um, stop or slow down. Okay, so now you can answer this question in a better way. That dislocation movements are impeded or strength decreases. Which of the option is correct? If you cannot speak answer, you can also write your answer in the chat box. So I will be able to know that you have understood this question clearly. So answer the question. It is dislocation movements. Okay. That is why the properties of nanoscale materials are much better than the bulk mechanical properties, which I say, because the dislocation, the which I mean, by dislocation means that cracks or fault in the material reduces. Okay. Question number third. Which of the following mechanisms strengthening effect can be eliminated? Can be eliminated by heating. Which of them Which of the option is correct? Grain size reduction, strain hardening, solid solution strengthening, or both A and B?
A and B, ma'am. Both and
Right. Because for the heating, this requires heating, if you know. We have we have read about the phase diagram, pressure and temperature dependence. So if you want to make a solid solution, then there is a role of temperature. So this option is already odd one out. Got it? So that is why these two options are correct. This is one of the way to solve the questions. Next question. The strain rate sensitivity index of a material is observed to be equal to 0.4. Which of the following comments about the material is correct? It shows plastic behavior, it shows superplastic behavior, it has high melting point, or both B and C. Which of the statement is correct? If you have a strain rate sensitivity, this is a symbol, and if you have that is equal to zero point 0.4, then which of the option is correct? You understand the difference between plastic and superplastic behavior? Yes or no? The way to differentiate between the material, which is plastic and superplastic, the value of strain sensitivity index is important. If it is less than zero point 0.3, then it has a plastic behavior, and if it is more than zero point 0.3, that means in this case we have value zero point 0.4, then it has a superplastic behavior. Got it? So the answer is this second option.
B option.
Yeah.
Second.
Process that can be used to make fine grained material while maintaining its external dimension. Which of the process, like hot rolling, high pressure torsion, equal channel angular extrusion, or both B and C? You have to answer that if stress is applied on a fine grained material, so in which of the process the dimensions will not change? Which of the technique will give you nano size material but the dimensions of overall material will not change? Understand this question if you haven't. We have a bulk material, right, and we have a lot of nano grains, multiple grain, one, two, three, multiple grains, and you have reduced its size. Now you have grains of this size, very small, so on, very small, small, small. Dimensions are same, but the grain size has reduced. Which option will help me to achieve this sample? Do you understand what is hot rolling? Yes or no?
No, ma'am.
No, sincerely.
Okay. That is what I want. That if you have not understood anything, you can ask the question. So hot rolling is a technique in which we have two rollers. Okay, these all are techniques which give you nanomaterials, right? You understand what is a nanomaterial? Do you understand the definition of
Yes, yes,
nanomaterial?
yes, ma'am. Whose dimension is below 100 nanometers. The material which are with dimension below the 100 nanometers.
Yeah. So tell me, if you understand the definition, then
Hello.
this length is 1 micrometer and this breadth is around 2 nanometer. I am naming this sample A. Okay, and I have another sample B. This is 2 nanometer and this is also 2 nanometer. Okay, size is not appropriate weight. 2 nanometer, 2 nanometer, and B. This is sample B and this is sample A. Which of them is a nanomaterial? It is 1 micrometer. Which of the material is a nanomaterial? A or B?
B, ma'am.
Material B.
Are you sure?
I think both, ma'am.
The correct answer is both A and B, because the definition you say that material in the dimension of 10 raised to power 9 nanometer meter, 1 nanometer is equal to 10 raised to power minus 9 meter. Okay, so one of the dimension, at least one of the dimension should be in nanometer. It is not necessary that all the dimension should be in nanometer. If one of the dimension is in nanometer, then it is also a nanomaterial. Do you understand? Both of them are nanomaterial.
Yes, ma'am.
So now you can answer this correctly. Answer this.
Answer A and B.
Yeah. I'm asking one more question. I have a particle of around say 30 nanometer. Okay. And I have a particle around 1500 nanometer. Or let's suppose if I have around 2000 nanometer. Which of them is a nanomaterial? A or B? What about Pushparaj? What do you think? Way to chemist saying A is the correct answer. What about you, Pushparaj?
A option, madam. A.
This is 2000, right?
Yes, ma'am.
So you understand, even if I write a large number in nanometer, but just writing the word nanometer will not tell me that it is a nanometer. Got it? You should have the range 1 to 200. Do you understand?
Yes, ma'am.
Even if I write 2 lakh nanometer, it does not mean it is a nanomaterial. You should look at the number. Now
1 to 200.
coming back to my point. So now the definition is clear. Now what we are discussing, that we are discussing the techniques to create nanomaterials. Fine. Specifically to make how to make nanomaterial. So these are the technique which is mentioned in these four options are one of the techniques. Are all three techniques belongs to the reduction of the material into nano size. But the condition which question says that the external dimension should be same. To answer this question, you should know what all three technique means. So hot rolling technique means, wait, wait. Hmm, if I have a space over here, I will use a space here. Okay. I have two rollers and material is rolled into this roller. A, whenever a material is rolled over, then it will become its thickness will reduce, right? If I have a thickness of around 10 micrometer, then I'm my thickness will at least reduce to some dimensions. It will decrease. Do you agree?
Yes. Yes.
So
Yes, ma'am.
so when the thickness is reducing, what is happening that the grain size earlier was grain the grain size was very large, but now
Grain
when
size
the
reduces.
so now when the grain size reduces and thickness also reduces, both the things are happening. Thickness is a part of dimension, so at least in hot rolling technique the dimension is not maintained, the external dimension is not maintained. Got it?
Yes, ma'am.
So this
Yes,
option
ma'am.
is
Got it.
incorrect. Now second option, high pressure torsion. What happens in high pressure torsion? where two very heavy weights are there, and the material is pressed between them, and it is pressed in such a manner that dimensions will not change. The stress which is being applied by this will just reduce the grain size, smaller grain size. You have a circular material, it will remain circular, nothing will change. You are pressing, so when you press that, if it is a stiff material, the dimension will not change. Do you understand? You are not rolling over it, you are just pressing it, so any other dimension will not change. So this is one of the right answer, high pressure torsion. Force is torque force is applied and torsion is applied, and then the grain size reduces. Next question, next is EQ channel angular extrusion. Equal channel. What happens in this? At a material is inserted into some this type of channels which is bent at different angles, different direction, but at 90-degree angles like this. And material is passed. You are dropping your material. So when it is passed, so through this regular passing and removing of from the channel, the grain size reduces. Okay. So when you put of this dimension, all the dimensions are equal all over the place. Do you get it? So dimension will not change because all the dimension is of the size of the material itself. So this also option is correct. So the right answer is both B and C.
Madam, in option 3, how grain size reduces?
In option 3, the grain size reduces in this way. It is being pressed, okay, by the angles. The angle at which it is moving forward, it is being pressed. The force is being applied, external force. You understand? Okay.
Yes, ma'am.
So shall I move? Yeah. Both B and C. Which of the following is not true regarding high pressure torsion? So now you will be able to answer this. Sample of sizes of several centimeter can be worked on this technique. Grain size reduces during this process, applicable in industry, and non-porous samples can be made. Is not true. You have to answer. Do you agree with option 1? Do you agree with option 1? Yes or no? It is saying that you can put any macro sample. Yes, this option is right. Yes, you are right. But do you understand what option 1 says? Why this option 1 is correct? It is, see, the technique is to reduce, to get the material nano size, so the material should be in bulk size. So it is saying that several centimeter of the samples can be used to put into the high pressure torsion technique, and it will reduce the material, right? Grain size reduced during this process, this is also right. And this is also a technical thing that non-porous samples are made. In both the technique, equal channel angular extrusion and high pressure torsion, non-porous samples are made. So option 3 is incorrect because this technique is on a very small scale. You cannot use in the industry application. You can just use in your labs, in research institutes, but not in at a very large scale. So that is option 3 is correct. C option is correct. Question, you have to match the following and which of them is correct. This you have to match its the strengthening mechanism with their property. Do you understand solid solution strengthening? Solid solution, like two different materials are mixed at under high pressure and temperature, under pressure and temperature. Mix is a very general term, are reacted at certain pressure and temperature. Suppose I have aluminium and I have to make aluminium nickel alloy. So I will put some nickel into it. So in such kind of alloy, maybe 90% is aluminium and only 10% is nickel. So what is it doing? Strain field interaction between dislocation and impurity atoms. I'm introducing some impurity atoms into the pure sample in order to strengthen its mechanical properties. So C is matching with third. So it means this option is incorrect. Now I have left with 2, 3 and 4 option. In grain size, yeah. So in grain size reduction, in strain hardening, what happens? Strain is applied on the material and there are some dislocations. The atoms, which was, suppose this we have a group of atoms like this, and strain is applied, and atoms gets dislocated from its initial position, and in this way the dislocations are piled up. It is B1. And which option is correct then? I'm left with only this option third. A belongs to dislocation movements limited extent. C. Yes. Got it? I've discussed the different types of dislocation, different types of techniques in previous session also. So you can see the recorded lectures and understand much better way. Which of the following characterization technique can be used for characterizing nanoscale grain boundary sliding? In the last lectures, I have shown you two samples, two images in which we can see the dislocation. So which was the technique I have used to tell you about the grain boundary sliding? Do you understand optical microscopy? You will be able to answer this question when you understand these techniques. So do you understand optical microscopy? Yes or no? This is an interactive
No, ma'am.
class. Okay. Optical microscopy you have used in your day-to-day life, like not in day-to-day life, but you must have used one time or the other. It is normal lens which we use to see things under the microscope. You have seen microscope, you can see things, some bacteria, some onion peels. Have you seen a microscope?
Yes.
Yes, ma'am.
So
Yes, ma'am.
yeah, it uses light around you, and then you're able to see the things under the
Yes,
microscope.
ma'am.
So that
Yes,
that
ma'am.
the technique which you're using, that is optical microscopy. Okay. So
Yes, ma'am.
through that you won't be able to see nano size things, because you are only able to see only macro size things, because the optical lens has some limitations. To see a very small thing, the lens should be very large, and to see nano things, a lens should be at least of 2 rooms. You cannot have such a big lens, and you cannot handle such a big lens, right? So optical microscopy cannot be used for nano to see nano particles. What about SEM? Do you understand? A scanning electron microscopy.
Yes, ma'am.
Yes, yes, ma'am. Scanning electron microscope, one of the instrument.
Yeah, you are able to see the things. You are able to see what? Morphology of the material, right?
Yes, ma'am.
Yes.
You are able to see the thing. You are able to see what is the shape of the nanomaterial. It is circular, it is triangular, or it is irregular, or it is cylindrical. These type of morphological shapes you can see, hmm, in the SEM. But what is the purpose of the question? The purpose of the question is to see the nano sizing with the grain boundary sliding. That means you are reducing the size, and side by side you are able to see that what is the effect. So it should be something in situ. In situ means uh, along with the time you're able to see the change throughout that till the experiment is running. So in situ, SEM is similar to TM, but the principle is different. You're able to see the 2D image in TEM, but much more higher magnification. In SEM, if you are able to see things up to say suppose 30 nanometer, in TM you will be able to see the nanomaterial up around even from 5 nanometer also, 2 nanometer also.
Yes,
Got
ma'am.
it?
Yes,
And
ma'am.
now
And resolution is also uh,
yeah, resolution also high. So grain boundary is in the range of nanometer only this range. This is the range of grain boundary. And you have to see the sliding along with the time. So in situ sample holder should also be there. You are dislocating the material, and you're able to see that how it is getting dislocated. That is why option 3 is correct. Do you follow all the options? Did you follow all the
yes,
options?
yes, ma'am.
Yeah, yeah.
Transmission electron microscope.
Equal channel Equal channel angle extrusion can be used to make complex shaped in partition industry. In sorry, machine parts. Sorry. Equal channel angle extrusion can be used to make complex shaped machine parts in industry. Yes or true or false? Then what is the correct answer? If it is false, then what is the correct answer? Your answer is right. It is false. Then which is the technique if I want to make some complicated machine parts, like very fine screw or very fine Allen key? This is Allen key, L-shaped keys or screw, very fine screw. Then which technique can be used? The right answer is
Torsion.
Electro
Tor-
no, no. Torsion is a technique to make grain size, to make smaller grain
Reduce.
size. But the question is, you have to make some shapes. And in torsion, shape is not changing. Remember? So if shape is not changing, how you will make different complex shaped? Do you understand? The correct answer is electro discharge machining. Discharge, EDM, short form. Do you remember this technique? I have explained earlier also.
There is any connection between with the nanomaterial? This machine have any connection? Yeah, any
Connection is that when the shapes are which is being formed, the tip is also of nanomaterial, the tip which is being used, as well as the particles which are which are being removed from the surface, that is also in nano range. What happens, I'm just explaining briefly, that you have some material, you have to make some particular shape, you have to cut out some screw shape like this shape, T shape suppose. An electric current, this is your uh, an electrode, and the tip is very small, so a lot of charge is concentrated over this point when current is applied, and this current, it produces plasma because where it is very high current, and this plasma is able to remove the particles. Like if we move the shape which we want, we move that electrode in that shape, and that is slowly and slowly it is removing that area, and hence we get very complex shaped. Did you understand how EDM works briefly? Yeah. So next question, in superplastic material, the yield strength at the neck is higher than the yield strength away from the neck. True or false?
True, ma'am.
Right. Why? Why it is true? What is happening that the strength at the neck? Do you understand what is neck? If I have this dog bone sample, so this is the neck, and this is your remaining material. The question is saying this part is much more stronger than this part. A part is much more stronger than the remaining part of the sample. But this is very small. Then why it has a very high yield strength? Think.
it becomes with nanomaterials. No? Neck is
Um, just repeat your answer.
it becomes with nano materials. Therefore, it is stronger.
Yeah, it is becoming nanomaterial. How? We make nanomaterials how? By reducing the grain size. So here when we put strain hardening, when you put strain on the material, then the grain size of this part decreases, and the grain part decreases, the material becomes strengthful, it becomes more strength because of the Hall patch effect. You have heard
Yes,
about
ma'am.
Hall, we have discussed the Hall patch effect. What it says, it says when we are moving from suppose 5 nanometer to up to 25 nanometer, the strength is decreasing. It means at lower nanometer range, the yield strength is very high. Followed? So this is what is happening. And that is why the properties of nanomaterials are important. This course, we are in this course because we want to understand how the bulk property, this bulk property is different from the nanoscale properties. Now we are using the assignment question. You see a plot over here, and question part A of the problem 1 says from Hall patch effect. This is a Hall patch effect for copper zinc alloy. Determine sigma and constant values from this plot. Now my first question before this. Here it is saying a Hall patch plot. Agree? Agree? This is called Hall patch plot. But just now I have told you Hall patch effect is this. It is saying this, but I am saying like this. Why I am talking two different things over here? I told you na, from 5 nanometer to 25 nanometer yield strength is decreasing. Here it is saying from if we are moving from 4 to 16 millimeter, the yield strength is increasing. The point is we have two Hall patch effect, one in macro range, one in micro range, and one in nano range. When we talk about nano range, it is a this kind of relation between yield strength and grain size. And when we are talking about micro range, like millimeter, micrometer, this kind of range, then the Hall patch effect is a direct relation. Understand? So it is important to check what is the dimension of this. Yeah, reverse. It is reverse. It is important to check the grain size. Both are correct, but the context is different. So let's solve the problem. So what is the Hall patch effect says? This is a yield strength, symbol of yield strength, constant, and grain size raised to power minus half. Now first our aim, we have to find these two values. To find these two values, if we apply linear relationship, this is our x, this is the y. I have to determine the slope. Slope can be determined very clearly. Suppose I take this 4 value and I take suppose this two numbers, big numbers. Here it is cutting it is cutting this point, and here it is cutting this point. It is some between the middle of the two. So it's a 50, then it can be 75, and it is if 150, then it can be 175. Are you following, students? We are finding the slope. We have to find the constant over here.
Okay, okay.
Yes.
Okay. Then slope will be, it is y2 minus y1, x2 minus x1. I have two values. For 175 megapascal, I have grain size of 12, and for 75 megapascal I have grain size 4. Putting these two values over here, tell me the answer. Solve this value. What is the answer?
100 by 8.
Yeah, 100 by 8. What is the answer in the decimal? It is a simple calculation.
12.5.
Right. 12.5 megapascal, and I have grain size in the denominator, so millimeter power half. So this is my slope. Are you following, students? We have got
Yes, ma'am.
our this constant value. Now our aim is to find sigma naught, which is very simple. Now you know sigma y. Take any of the point. You know this point. For 12 you have 175 megapascal. So I put it 175. Sigma naught. Now you know slope. You put 12.5. Okay. You know the grain size of 175. It is 12. Then what is the sigma naught? 175 minus 12.5 into 12. What is the answer? Tell me the answer. 12.5 into 12. What is it? It is 150. This gives us 150. 150, 175 minus 150 is
25.
25.
25.
Right.
25.
25 megapascal. So we have solved the problem 1. This type of numerical will come in your exam. I have discussed in previous session also. I am discussing with this plot over here again. Now the second part. Predict the yield strength of this alloy if the average grain size diameter is this. 10 raised to power minus 3 millimeter. Can you solve this question now? What is the approach? Who will tell me? What is the approach to solve this question? You know the equation. Now you know the sigma naught value. You know the ky constant. You know the grain size which is it is talking about. You have to find this.
Just
Will
a
you able?
substitute in that equation.
Yes. So let's do it. Sigma naught y will be equal to 25 plus 12.5, and the diameter is 10 raised to power minus 3 minus power half. Solve this question and we will discuss the answer in the next class. Do you follow? Everyone follow, I
Yes,
hope.
ma'am.
Now, next question. Consider a cylindrical specimen of steel alloy. It's a kind of alloy we have of 10 millimeter in diameter and 75 millimeter in length. Long was pulled in tension. Determine its elongation when pulled with 20,000 Newton tension. You have this plot over here. This is stress strain plot. Do you understand what are these different? What is this point called? What is this point called? What is this point called? What is point C, B, and A? What is C point? What happens at C point? Okay, just see the plot. Read the plot clear. You can read the plot. If you don't understand the concept or if you do not remember anything, you can read the plot. This is
Breakdown. Break point.
yeah, fracture point, break point. What is A point? What is happening at A?
Stress point.
What is it?
Stress point.
Deformation.
Deformation is happening, but A point is called yield strength.
Elongation. Oh, yield. Oh.
Yield strength. Then what is B point? What is B point? Is it? It is ultimate strength. Okay,
Am I
maximum it
not get
can.
what is B point?
Ultimate strength.
Ultimate.
It is maximum yield strength, and then the ultimate strength. After that, it will on to the path of fracturing. So we have understood how to read a plot. Now, using this knowledge, answer the question that how you will find that how much elongation is happening when we put at least around force of around 20,000 Newton. Newton means we are applying some stress. Let's solve the question. Our approach is we know stress, we will find strain, and when we know strain, we will find the elongation. Elongation is called delta L. What is stress? Force upon area. Agree? Now you have to solve the numbers for me. I have force of 20,000 Newton. Now I have to calculate the area. The specimen has a diameter of 10 millimeter and length. So if I have this cylindrical, so this part is having force on the tension. So pi r square. That means pi into 5 millimeter. Diameter is 10 millimeter. So area will be 5 millimeter. What is the answer? Tell me in Newton millimeter per square unit. Just solve the answer. 20,000 divided by pi into 5 into 5.
254.
254. Right. Yes, you are right. But our units in Newton per millimeter square. And the values are over here is given in megapascal. So we need a unit conversion. Got it? 1 Pascal is equal to has unit of Newton meter square. This is a unit of 1 Pascal. If I want to change into millimeter, then I want what I will do. 1 meter square is equal to 1000 millimeter. Since I have power 2, then 1000 millimeter. How much power I have? 10 raised to power
6.
6. Got it? Now 1 Pascal is equal to 10 raised to minus 6 Newton per meter square. And if I want to change, in megapascal, then a unit will become 254 megapascal, because 10 to the power 6 will cancel. Got it? Now our stress is 254 megapascal. Look for the 254 megapascal. We have 0 to 1000 reading. This might be 800. This might be 600. If we equally divide, this is around say 400, and this much part will be around 200, and 250 will somewhat lie over here. Are you following my pen where I am marking? Are you following it? Yes or no?
Yes.
Then this value will give the strain, equivalent strain. I have applied 254 megapascal stress. From the plot, I can find that its equivalent strain on the base of division of unit. This is around 0.01, and it is very small region, so I am considering it very small, 0.025. This is 0.01. This point will be 0.02, or say not say 5. Let's be this much only, 0.02. Fine. Now I know stress. Now I know strain. Now my aim is to find the elongation. What is the formula of elongation? Strain is equal to final length minus initial length divided by initial length. This is delta L, and initial length is already given 75 millimeter. Can you find the elongation now? Having this value 0.02 divided by delta is equal to delta L divided by 77 millimeter. Tell me the elongation. What is the elongation? How much is the elongation? What is the answer? This is an interactive class, so you should be answering this small question. Tell me the answer. This is very okay. So answer is around 0.15 millimeter. This much elongation happen when you apply at least 20,000 Newton. So it must be a higher yield strength, na? Only so much amount huge force applied of 20,000 from 75 millimeter. It has changed only around 75.5 millimeter. So you must have got an idea that the alloy was a very high yield strength. That is why much elongation did not happen. Okay, class. I hope you have followed this question very correctly.
Yes, ma'am.
Yeah. So if I say, if I want to know the this value must be 500. megapascal. Then what is the corresponding strain? And tell me if I'm giving the stress of 500 megapascal, tell me the strain and then tell me the elongation of the same specimen. Solve it. This is a 500 megapascal. This will be its value. Is it 0.005? What is half of it?
0.0025.
Yes. Now tell me what is the elongation if the measurements remain same of 75 millimeter. What is it? Answer, you have 2 minutes to answer. So it is right now happening 7-7. Give me answer by 7-9. It is very simple mathematics. Have you followed this question? What is the answer? Answer is answer is 0.025 into 75. Elongation will be of 0.875 millimeter. Followed? Okay, you don't want to answer. Next question, next topic. So we have discussed some assignment question, we have discussed some problems. Now we'll discuss some conceptual questions. So what is the picture tell you about? Which technique is this? Which technique is this?
Hardness testing.
Are you telling Wixer hardness?
Yes, ma'am.
No, it is not. See, there is a disc, there is a motor. It is flat like shape, and if this is my sample, it will rotate.
Pin. That is pin. What was that?
Yeah, you are near to the answer. Yes. Try to recollect it.
Resellers. Pin fetch. Oh, no.
It has disc, it has pin. Yeah, what is it? Pin on disc testing.
Yes, ma'am.
See, it in real life it is look like this. In lectures you have seen the schematic diagram, but if the instrument comes before you in real life, you won't be able to recognize that well. So that is what in real life the instrument look like. The lecture which you saw, it was for you to understand its fundamentals, how it works. But in actual, it has so much of techniques and so much parts are there. And it did talk. See here, this is in screen. You can see smaller version of it. From this computer, you can control what are the three factors on which that pin on disk testing is uh, is built? What are the three factors it get affected by? There are some factors, right?
Yes, ma'am. I'm not able to read. Grain size.
No. That our test will be affected if I change those parameters. What are those parameters?
Rotation. RPM.
Right. Rotation. Next, there are three factors. What is the second factor?
Pressure.
No, there is no such pressure we are applying over here. It is rotating, but we are not applying any pressure.
Dimension or distance of the sample.
It is related to environment.
Okay.
So now you can guess in a right direction. It is an environmental effects. Temperature. Temperature is very important. You are thinking of the samples which are solid, but pin on disk techniques can be used on wide range of samples from ice to grease to oil to food to steel. Such a wide range of samples are there. You understand? So for to correctly study wear test, we are studying through pin on disk testing. We study wear behavior. Wear means how the particles loses its weight when some stress is there on the sample. Understand? So when for the wear test, temperature is important. Third factor. What is the third factor? It is also related to environment.
Not able to recollect, ma'am.
It is anyone? Anybody else? It is humidity. That is very much important. Why it is important? Now I have told you the factors. I have told you yes, rotation is important because the speed at it is which is it is rotating, it will affect the amount it is losing. I've told you about the temperature because we are using wide range of material. Humidity. Why the humidity plays such an important role on this fear test? Why? Humid moisture comprises of what? Humid moisture comprises of what? Water and oxygen.
Yes, water and oxygen.
Now can you tell me the answer if I have given you the enough hint? If I have water and oxygen in the environment and I'm doing a wear test, how will it affect my sample? Obviously, it will be if it will affect my sample. How will it do so? It is very simple. Now, do you understand how this pin on this testing works? Do you understand how do we perform a wear test? Yes or no? Then you will able to answer this question first.
Not exactly, ma'am. But
Okay, so we can explain over here. Let me see if my eraser is working. It is not working. So I will explain here on this page only. I have a disc, I have a motor attached which will control the speed. This is the center C. Here is my sample of which I want to perform a wear test. Okay, and a rod is attached to it. Is in the schematic we do not mention this, but here in the diagram I'm showing you, which will follow its movement. Now we are rotating the sample, suppose at very high speed, very large speed. It will rotate and slowly some part of will deform, some part of will, if I do it very fast and very rigorously, then some part of will, some smaller granules will come out of it. Did you follow? Just imagine if you put some rolling some sample very harshly, it will lose it, it will break or it will lose some granules. Agree? That is the basic concept. Yes or no?
Yes, ma'am.
Yeah. So it will lose some weight, and the depending upon the speed, or better we say how much rotation it has done. So it is called sliding distance. The how much rotation it has done to wear, to get wear, how much rotation it has done to wear, that is called sliding distance. Okay. Now on the y-axis we have loss, weight loss. And how at the, so how much distance it is covering, that much weight it will lose, so it will have a direct relation. Followed? If I have a strong sample which does not wear easily, then the sample loss will be less. See, of the same distance cover, for sample A I have this much loss, for sample B I have this much loss. Followed? So in this way we measure the wear test through pin on disc testing.
Ma'am,
Agree?
from your plant, the material B's have a high wear resistance compared to C. Huh?
Uh, Sorry, repeat your first line.
From your graph, you draw two material. One is named as BC. So the material B has a very comparatively C it has a weight loss, low. It does have light weight loss. So the material B have a high wear resistance.
Yeah,
Is it? Okay.
yes. So B is a better material for us to work upon. So in this way we analyze pin on disc testing. So what was my question? The role of humidity on this wear test. So for this we have to understand what is happening at the bottom of this, the sample which is here. Whatever is happening, it is happening at this smaller portion. If I zoomed it, it is divided into three parts. Here it is weird part. Here it is deformed, smaller. I have zoomed it. Deformed part, and here it is undeformed part. So from this region we are losing our, the sample is losing its weight. Fine. So what happen when we have a humid condition, and this is a, and this has a, if it has some, if it is iron based material, so in humid condition this part will get corrode due to oxidation of iron, and the oxidation of iron will affect the other parts, other layers also, the layers above it. Followed? Do you follow this? If I have very humid condition, this weird part will affect it, and oxidation will start. And slowly when the the turn of deformed layer comes, then also it will get oxidized, and slowly it will affect our whole specimen. And when you perform the wear test of same sample after some time in different humid conditions, then I will get a different wear. I will get different values for wear test, and I won't be able to establish some conclusive result. That is why for pin on disc testing, three factors are very important: rotation, temperature, and humidity. I hope you have followed. Have you followed this technique, students?
Yes, ma'am.
Okay. Other students, if you cannot answer verbally, you can write in the chat box also. Okay. So moving on to the next slide. Now we will discuss about vacuum spray technique. Tell me, I have discussed the schematic diagram for pin on disc testing. Now explain the recollect the schematic diagram for vacuum plasma spray technique and name all the parts involved in it. What are the parts? What are the parts for the vacuum plasma spray technique? Have you remembered this? Are you able to recollect it? See, to create a plasma, there should be a voltage difference. Then I need an electrode, which is called cathode over here. If cathode is there, then it should have anode. Okay. Now, here are my larger particles, large size particles. Since plasma is involved, then there should be a chiller system also. So it is liquid nitrogen, and there is a gas. Because this all should be performed in high vacuum, then argon gas should be flushed into it. And here is my substrate, on which these nanoparticle will get deposited, and we will get a target. It has very fine particles, but large, but in a just kind of a block. We don't have very smaller distinguished particle, but we have a collection of particles, a block of particles, nanoparticle, and that is called target. Here plasma is generated because of the interaction of anode and cathode. Our nanoparticles, our large bulk particles get deposited and they move through a carrier gas over here and get deposited on a substrate, and some particles get deposited. And there is a chiller system which uses liquid nitrogen. So how many parts do I have in this technique? Count the number of parts. You can do this one at least. Now can you name the parts from the schematic diagram? Yes. I have substrate, I have anode, cathode, liquid nitrogen, argon gas, target, 1, 2, 3, 4, 5, and our sample. 6 main parts are there. Mention the following VPS, vacuum plasma spray technique. You have to tell me the range. In what range all this process happens. So for various factors, you have to tell me the range. Plasma temperature range. What is the range of plasma which is formed in this technique? What is its temperature range? Tell me. Students, please be involved in this session, otherwise it will not be of any use for you. If you know incorrect answer, that is okay. I'm here to correct you. I'm here to tell you, but at least get involved in this session. What is the plasma? What is the temperature range of the plasma formed in this vapor vacuum plasma spray technique? Is it 250 Kelvin? Is it 200 Kelvin? Do you agree with these two values? Do you agree with these value? Way to Chem is agreeing with these two values. Who all agree with these two values? Correct answer is 20,000 Kelvin. It can range from 10,000 Kelvin to 15 Kelvin, and in some case 20,000 Kelvin. This is the temperature range of the plasma. This is our room temperature is at 273 Kelvin. Sorry. 300 Kelvin is the room temperature. And 250 Kelvin is very around 0 degrees Celsius. The range, since I'm using a chiller system, that means the temperature is very high. We use coolant because to cool down the heat. That means the temperature is very high. So this is that temperature. Now things are getting heated up. Then what is the cooling rate? Who will answer the cooling rate? You can give your values in the range like this, which I have told you just now. What is the cooling rate for the substrate? Or till what temperature does liquid nitrogen is able to cool down? Why do I need a cooling rate? Yes, it is correct from a machine point of view that we are generating plasma, but why it is, what is an what is another reason related to the nanomaterial that we need such a liquid nitrogen as a chiller system, in our chiller system? What is the purpose of liquid nitrogen over here apart from acting as a coolant? What is the purpose? Purpose is to arrest grain growth. What will happen if grain growth does not stop? What will happen? If grain size is growing, is increasing, then what is happening? It means our material is not turning into a nanomaterial. It is staying as a bulk material itself. To convert into a nanomaterial, we need to stop the grain growth. We need small grains, and this liquid nitrogen helps in stopping that grain growth, arresting that grain growth. I hope you have followed this. Then it it is able to cool the temperature from around 15,000 Kelvin to 70 Kelvin. See, from 15,000 it is able to bring the temperature around 70 Kelvin, which is equivalent to around minus 96 degrees Celsius. Such a powerful coolant it is. And that is why this technique is important. What is the velocity? Velocity of the particles through which it gets settled over here, settle on the target, on the substrate I mean. What is the velocity of the particles? What is the velocity of the particle? It is, since it is a fluid like particle, that is why the unit of velocity is not, it is not meter per second. It is, the units are Mach, very high speed. Mach is used when we are describing the velocity of fluids and the speed is very high. Then velocity is Mach 1 to 3. Sample range. What range of samples can be poured into the vacuum plasma spray technique? What is the range of the samples? Anyone who will tell me? Priya or Pushparaj? Any idea about the particle size? Any idea about particle size? How much size range of the particles can be put through? Can be used in this? Can be used in this technique?
No, ma'am.
But particle size remains constant, ma'am.
It is constant. Yeah, I agree. It is constant, but there should be some range, na? What is that particle size? If it is constant, then what range of the particle size can be put?
Nanometer range?
No, nanometer, we are forming. We are forming nanoparticle here. The particle are in bulk size. What is that size range? We are converting bulk to nano. The size range is 5 micro to 80 micrometer. Okay. If I use less than 5 micrometer particle sample, then it will clog the pores of the system. It will create clogging into the system. Some small, if there is some small space, it will block that site if I use particle less than 5 micrometer. Okay. Okay.
Yes,
Now,
ma'am.
now tell me then why I am using a limit of 80 micrometer. Bigger size particle, what problem will bigger size particle create? If I use particles of greater than 80 micrometer, what is the problem they are creating? What is the problem they are creating? Yes, anyone? Think what is happening to that particle. The particle is coming down, plasma is being created. If I use particle of bigger size, will plasma will get created easily? If suppose I have a particle of 10 micrometer and I have a particle of 100 micrometer, which will get easily converted into nanoparticle? 10 micrometer, 100 micrometer. Easily it will be 10 micrometer will easily get, because size is small, sample is small, amount is small. So it will heated, it will get heat faster than 100 micrometer. Obviously, it will get heated easily, and it will easily get convert into the nanoparticle. If I use larger than 80 micrometer, what will happen in that short interval of time? It will not get heated completely, or it will get partially heated. And when that plasma is moving towards the substrate, some particle will be of nano size, some particle will not, some part of it will be of nano size, some part will not be of nano size. In this way, it will create some non uniformity will be there of on this block. Do you follow this reason? Do you understand what is the limitation of using less than 5 micrometer and greater than 80 micrometer in this technique? Is it yes or no? Have you followed this? Pushpraj, Priya?
Yes, ma'am.
Okay. Now you have understood all the factors, you have understood the schematic diagram. Then tell me, what is the purpose of vacuum plasma spray technique? Why we are reading this? Why we are putting so much effort into this technique? What is the purpose of this technique? Why we are from getting micro particles, we are creating a block of nanoparticles? What is the purpose of this technique?
To improve some properties.
Which properties?
Hardening property, madam.
No, wrong answer. Think of the process. Properties will get increased. Yes, you are right. We are moving on to the nano range. But why we are creating a block? Suppose this the sample which are putting here is of like they are like bead like structures, beads. And what we are getting in return is the block, a block of nanoparticles. Why are we creating a block? We can use nanoparticle
Strengthen
bead.
our material.
Sorry.
Strengthen our material.
No, the right answer is that if I want to study, suppose I want to study the pin, I have to study the wear test of a nanomaterial, suppose zirconium oxide. Okay, if the nanoparticle is of suppose size of 2 nanometer, this 2 nanometer will not be suitable for this machine. Agree? You won't able to follow how it is rotating, what is the sliding distance, what is the weight loss in mg. You won't able to will you able to measure the size of will you able to measure the weight of the 2 nanometer size particle? Yes or no?
No,
No.
no.
No. So if you want to study a wear test, suppose you want to study a wear test for the nanoparticle zinc oxide, you won't be able to study if it is a single particle. Agree?
Yes, 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 ma'am.
So we are creating a block of 2 nanometer particle, and this block can be used in wear test to study its wear test. Agree?
Yes, ma'am.
So for such kind to study, since the properties of nanomaterial cannot be studied uh, if we are using just a simple nanoparticle, we need a block of particle to fit into our instruments, to fit into the suitability of an instrument.
Yeah, yeah. Now I totally get. Okay.
So that is the purpose of using this technique. Okay, that block can be used for wear testing because it has got length, it has got weight, it has got right amount of height, everything. You can maintain its weight loss in mg because it might be of grams, but single nanoparticle is not suitable for this machine. I hope you have I have covered all the things over here. If you have any doubt, you can say, otherwise I can proceed.
No doubts, ma'am.
Okay, okay. Now the next slide. Here I am discussing one of the papers which has used vacuum plasma spray technique. It is of Elsevier publication. This is a paper and the journal name is Acta Materia. Materia. The paper name is Synthesis of Bulk Nanostructure Aluminium Alloy Component Through Vacuum Plasma Spray Technique. It is published in 2005. That it is that old paper. But in this paper you will study. You have to follow. I have explained you so much, lot of factors, lot of things. Now keep those factors in mind and see how it is used in real life, how it is used in research, how it is used in labs. Okay, keep all these factors in mind. So I have prepared the slide in a way that you're able to follow one thing after the other. The questions are arranged in that format. See, it is this research on this topic has been done in Florida, Orlando, USA. This is a USA based group. So what it want to study? It want to study the bulk and it it has the bulk aluminum alloy and it converted into nanostructure. Bulk nanostructure. Understand the word. The grain size is small, but it is a kind of a block. Do you understand this bulk nanostructure word? It is just like a target. They are making a target of aluminum alloy. Just not of aluminum, but aluminum alloy. Followed? I hope everyone has followed. So, they have taken a material. What is their sample? What is their sample? Their sample is aluminium silicon. Their sample is aluminium silicon. Aluminium silicon has 21% aluminium. It has around Al21, silicon 2%, nickel 1%, and copper in the remaining percent. This is the aluminium silicon. So they have used this as their sample to put in the machine. So obviously this sample will be of micrometer range. Yes or no? If you agree, you can thumbs up. If you cannot speak, agree. The sample which I want to put in the vacuum plasma spray technique will be in a nano range or a micrometer range.
Nano range.
Pushparaj, I have to put the sample into the machine. The sample I have to put, so it will be in micro range or nano
Micro
range.
range. Micro range, madam.
Do you have still have confusion in this technique, or it is it all right? Have you followed why I am using micrometer? Did you follow?
Yes, ma'am. Yes, ma'am.
Okay, just give me a minute. I'm just coming. Yes, the battery was low. Wait. Okay, so it will be a micrometer range. So if I want to confirm that it is of micrometer size, then what technique should I follow? If I want to know size of the sample of aluminium silicon sample, then what is the technique should I follow? What technique should I follow? Is it SEM? Is it TEM? Or is it optical? Which one?
Team technique.
Pushparaj, TM is used when I have to study even the particle of at least 20 nanometer to 1 nanometer. I have to study micro size particle. Which technique I will use? I will use SEM. See, why TM cannot be used? You agree that it has a higher magnification? Okay.
Solution higher magnification.
If I have a micrometer particle, suppose this is its structure, and I'm putting it in under a TM, and TM it is used for 20 to 1 nanometer. Will you able to see this whole particle in TM or some part of it, some nano part of it?
Some nano part of it.
So this will not give us a true picture of TM of my sample. That is why TM cannot be used. Okay.
Yes, ma'am.
And an optical millimeter range particle are used. Micrometer is smaller. Okay, so that is why optical will not be used. It won't be able to see anything. We won't be able to see anything under the optical microscope. So the optimum appropriate technique is SEM,
Yes,
scanning
yeah.
electron microscope.
Same technique.
So this is the image, the micrograph which you're seeing on your right. It is an SEM micrograph, and this is the alloy particle, aluminium silicon alloy. And what is the shape you are able to see in the micrograph? What is the morphology? What is the shape of aluminium silicon alloy? Is it rectangular?
Circulars.
Yeah, spherical we say. Spherical. Circular is 2D, spherical is 3D. Okay.
3,
Now
3D.
now tell me the size of these particles. Scale is given over here. It says this much size means 200 micrometer.
200 micrometer.
200. The size of the particle is 200.
No,
Yes, see, this is a scale. The scale, it says that this much size, this much distance between the 2 points is 200 micrometer. And if you see, the particle is of, if this is the diameter of my particle, it is around half of it.
half of it,
Then it is 100
100,
micrometer.
200.
Yeah, 100. If we put that particle on the scale, then it will be around half of that scale. Half of the scale will be 100 micrometer. Then that means the size of the sample which we are using is 100 micrometer.
Yes, ma'am, 100 micrometer.
Yeah, it will be less than 100 micrometer if I say. It is saying 75 if you accurately measure. Okay. I was just giving
Yeah.
the idea how to read a micrograph. It is exactly 75 micrometer because we cannot use more than 80 micrometer, remember? So it won't be 100, it will be 75. We clearly, if we correctly measure it. Followed?
Yes, ma'am.
Okay. Now they have performed TM. This is a SEM and see this is a TM. See, in this TM you cannot see the size of the particle. That is what why I was explaining you earlier. You won't be able to see the size in TM. Okay. So that is why SEM is a correct technique. It will look like this. What is it showing? That since it is an alloy, some region will be aluminium, some region will be aluminium based, some region will be silicon based. So it is telling that these are the silicon particles and most of them are aluminium silicon grain. There are some planes over here, twin planes, which is called, it's just talking about the properties of the aluminium silicon. And what is the scale? 100 nanometer. Okay.
Yes,
This
ma'am.
is the this is a difference between two techniques. You should know what you want to see, what you want to perform. Accordingly, you have to choose your technique. Now, what they have done, they have taken their sample now. Now they have to perform their technique. So what is it saying? What is paper saying? Paper is saying VPS forming is a thermal spray process carried out under reduced low pressure because it is carried out in vacuum. I told you it is carried out in vacuum and argon gas is flushed So it is reciting same thing. Reduce or low pressure to fabricate coating and near net shaped structures of alloy, intermetallic, ceramics, composition, functional gradient and material. This is a definition. It uses extremely high plasma gun of this temperature range. See, these values are not defined by me. These values were tested and then into the textbooks. Scientists perform these are scientists, these perform these techniques and get us give the values to us, and then we are able to know that in what range it will work. So that is why these information are taken from these kind of papers. Produced between two electrodes, cathode and anode, which I talked about. The powder particles get melted or partially melted, experience an appreciable amount of heat and are deposited onto the substrate with a high velocity of Mach 123. Followed? Now you are able to understand this language. You won't be able to understand this language until and unless I have discussed this. I hope you're understanding. Okay. Now, the what is the name here? I have highlighted the name of the machine. Name of the machine is the spraying. This name of the spraying machine is Plasma Process Inc. Huntsville, Alabama. It is manufactured in Alabama, employing a 4-meter tall VPS chamber. 4-meter tall. The chamber is VPS. The VPS chamber is 4-meter tall and is made up of this company of, and the power is 140 kilovolt. So much power is applied with CNC motion control, and a Paxer SG100 plasma gun was used for spraying. Okay, now these are the specification of vacuum plasma spraying technique. The table here, some values are given. The primary gas argon is used, which has pressure of 35 psi. Secondary gas helium is used, 110 psi. Powder carrier gas argon, same as I told you. Arc current 400 ampere. Arc voltage 35.4 volt. The distance between from the plasma to the substrate 10 centimeter. The chamber pressure is 650 torr. Here, this is the plasma spray deposit which we got. Then what they did? They want to measure its mechanical properties. Then through EDM machine they cut into the shape they wanted. Like they cut into this rectangular shape. They like now this shape they have performed, and and from this finished shape they will check the tensile strength. So you can see schematic showing machining of tensile test sample from VPS deposited aluminium silicon cylinder. This is the finished tensile sample. Moving on to the results and discussion part. Here they have performed XRD and characterize it, and they are able to see that it is an aluminium silicon based alloy. This is a SEM. It is of 20 micron scale. Here intersplat boundaries, you can see the splat which occurred on the substrate. It has taken note of it, and we have got intersplat boundaries. How these boundary works in this schematic diagram you can check. Here I got first splat, then second splat fall over it, and that the region, the intersection of these splat, there is a dynamic sintering, because this is little cool and this is still heated, because it has recently got out of uh, the through that fluid.
Sorry to interrupt you, ma'am, but you are just pointing out towards the junction formation between the silicon and aluminium deposit.
Yeah, it is a junction of the two splats.
Yeah, yeah, I got it.
Okay, okay. Now, in another image, they have discussed the different possible model of fracture of intersplat and intrasplat. Intrasplat between that single intrasplat fracture means in the single splat itself, we having some um, fractures, and the
Uh,
intrasplat.
the thing is, actually, while forming a junction, the material may be experiencing some fractures near the junction, and I think the best way to distinguish any such material characterization is to do EBSD, electron backscatter diffraction pattern. So you will get some idea about the uh, you like you say Miller indices pointed upwards to the plane and downwards to the plane, and distinguish between these Miller indices, you will get some idea that in which direction your aluminum metal nanoparticles are aligned and your silicon particles are aligned. So combining this, you will get an idea about your fracture line.
Yes, you have followed it very correctly, and which you were saying that third image explained that EBSD pattern. So they have taken and discussed the aluminum and silicon rich grains to study those fractures. That is why they are able to study intra and intersplat fractures. So not discussing in much detail, I will move on to the another slide. Here they have taken the TM of that aluminium silicon nanoparticles which they have formed, and we are able to see grain like structures over here. You can see that scale is of 200 nanometer. This is an electron diffraction pattern, and you see that these Miller indices are very much are will match with these XRD Bragg peaks. They have taken EDEX, elemental dispersive X-ray spectroscopy, okay, and they have found which was initially made of silicon, aluminium. It says some parts, some nickel, copper is also present, some amount of gallium is also present. So they have already described in their material section experimental procedure. So it is just reconfirming we are just reconfirming that we have got all the elements and right kind of alloy. So it means homogeneous distribution, nano-sized, ultra-fine primary silicon and aluminium matrix grain with EDEX spectra is mentioned. This is what I was talking about. Homogeneous distribution is there. Now, you can see how the grain size is distributing. Obviously, we have performed VPS, so it should be in nanometer range only. Most of the particles in the range of 20 to 40 nanometer, but some particles are also in the range of 50 to 80. So they have already mentioned the range. The lower range is 25 to 50 nanometer, that is lower range, and the upper range is 60 to 90 nanometer. Now stacking, the figure 9 explains the stacking fault in VPS form aluminium structure. We can see there are some faults As usual, TM is used, and this whole of is the whole of is it is eutectic aluminium silicon grain. This is the stress strain curve which we have discussed earlier. We can see there is a linear relationship. It says if you follow this figure, the tensile strength is of around 345 megapascal. That means after that deformation, plastic deformation will happen. Okay. An elastic modulus which we get from the slope. The elastic modulus which we get from the slope is 82 gigapascal. This curve is like this, right? So this part is mentioned in this plot. Now, what are the concluding remarks? The presence of nanostructure eutectic aluminium silicon grain is of 25 to 100 nanometer, that we have understood. Figure 7b plays a significant role according to the Hall patch effect. This is the Hall patch effect. No, Hall patch effect is grain size to grain size to yield strength. Relationship enhancing the tensile strength of VPS formed deposit. It is worth mentioning that the grain size in the VPS deposit does not fall in the inverse Hall patch regime, where the yield strength decreases with the decrease in the grain size. Obviously, because the range of the particle is 25 to 100 nanometer. For the inverse Hall patch effect, there should be 5 nanometer to 25 nanometer range. This is the table 2. They have compared the strain, ultimate tensile strength, elastic modulus, and micro hardness with other two papers. We can see the micro hardness which we measure through Victor's hardness is 551 plus and minus 14. Elastic model as earlier mentioned 82, and the tensile strength is so high if they have made from VPS. Earlier it was made from cast alloy, now they have made from conventionally cast method. They have made through uh, VPS. We can say through a hot extrusion also we get high yield strength, but the strain is also high, 7%. But in this case the strain was so low, around 0.43%. And with this let's end this today's session. We will continue and discuss the remaining topics in next session, and we'll also discuss the assignment and more conceptual problems. Thank you.